just a few things before I forget again. Let's look at the PDF. Here, that will be the equation sheet that you can use for the test. And there is another one you can bring also, which is more algebra based. But this one is really good. It took me a long time to find one that I like. And you see, it's calculus based. So this is physics 2. Okay, so you can see a little bit of calculus because, at least vector calculus, because you have the cross product. Okay, so make sure you get used to this equation sheet that you're going to start using them at least for the assignments, and then you can bring them for the test. Which takes me to the second thing. You need to review vectors. Okay, so if you forgot from physics 1, you need to know how to add vectors using components. Okay, adding the x component, the y component, finding the magnitude and the direction. And you have 2 very good tutorials in my Dropbox. So review that because I cannot take as much time that I did last semester. Okay, I suppose that you already know those topics. So review, adding vectors, it's in Dropbox. You have two tutorials. One is part 1, the other one is part 2. And then when you get some more time, you can review dot product and cross product. So if you are in engineering anyway, you will have to take vector calculus at some point. So it's a good prep. Okay, the other thing that I forgot to tell you, I have posted an assignment for next week. So maybe we didn't cover enough material yet, so you can wait, but you can start the assignment and then you save, and it will be saved in Canvas. Okay, you have 2 attempts. So for the first attempt, you have to do it on your own using the textbook and the slides and your notes and study group if you want. And for the second try, you have tutorials in Dropbox. Or you have ChatGPT, but of course, don't trust ChatGPT too much. Is that clear? So if you are in engineering, you really have to use your textbook. You see a textbook, you can open it. It opens. And then you go to the right unit, which is electrostatics. That will be the first chapter of physics 2. And then you read over, right? You skim through, and then you do the solve problem. So you hide the solution and you try to do that on your own. It's good for your brain plasticity, and it's good if you want to go into engineering. But you need to open your textbook because we don't have enough time together, and I don't have a TA. You know, if you go to some very big schools, you have the lecture and you have the TA. We don't. So you have to do work on your own. Is that clear? So that's a motivation talk. What else? Okay, for the pop quiz, I want to make sure that something maybe I didn't underline enough. Okay, so if we talk about conductor, right? You have conductor, insulator, and semiconductor. So in a conductor, for example, if you have a metal, so then the electrons here on the outmost layer, they are free to move, and they do. So a metal, the structure will be more like a lattice. So that's the question on the pop quiz, I think. So I want to make sure you get it right. So it's like a lattice, and the electrons, it's like a sea, right? It's like an ocean. So all those electrons, they are not tied to their nucleus. They are free to wander around. And because of the temperature, they move randomly in all directions. Now, if you apply a voltage to the conductor, then they will all start to drift in one direction, okay, because you apply a voltage. Otherwise, they move around here, right, randomly. So there is thermal motion. They always move around unless you are at zero, absolute zero. Okay, so I wanted that to be clear. And then you have insulator. So the gap here for the electrons to get to the conduction band and to respond to a voltage is too big. They cannot make that gap. And then you have semiconductor, where there is a very small gap, and that's how you can control the current, right? You give a little boost, and those electrons, they can make the jump. So then you get 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, right? That's the idea of computers and all the technology that we have today. Yes. The metal, yes, it's a conductor. Oh. So all metals are conductors. And the electrons can be responding if you apply voltage, right? You're going to have electricity flowing. Okay, the other thing that I wanted to make sure is I told you about the Leyden jar, which is the ancestor of what we call the capacitor. And the capacitor is everywhere in any circuit. And the way it works, it's two electrodes, right? So I just wanted to show you. We're going to get to that. It's just for you to understand how it works. So you have a power supply. Let's say you have a defibrillator. So you're going to connect the electrodes to the power supply. Okay, so it's going to be charged. So here you have a separation of charges because you are providing energy. So that energy is being used to separate the plus from the minus. They are not happy because they want to get back together. So you are charging the capacitor, you are charging the defibrillator. Then you see you can open the circuit, and that is a way to store charges. That's how the first Leyden jar worked. And then you can connect that to a load. The load can be your heart, for example, or it could be someone that you don't like. And boom, all that energy is being burnt out. Okay, so that's how a capacitor works. That's how defibrillator works. So you discharge it across your heart. There is an electrical current, and the heart hopefully will start pumping again. Okay, because I think there is two questions. So I talk about that. Textbook, you need a textbook. And okay, so we stop there. Okay, so that will be the elementary charge. Okay, the unit is Coulomb. So the charge of an electron and the charge of a proton is the same. The unit is a Coulomb. That will be 1.6 times 10 to the negative 19 Coulomb. Okay, we'll talk about that. And so we're going to start with electrostatics. So static electricity, it means it's the branch of physics that will study charges and the forces between them. And in the human body, if you go to medicine, for example, everything is electrical in nature. Okay, everything that's happening at a very small scale in the body has to do with charges, how they interact with each other, and how they respond to electric field. Okay, now the thing that you have to understand is that the charge is quantized. So if an object loses an electron, it's going to be positive, right? If it gains an electron, it's going to be negative. Protons don't move, only electrons. But electrons, the charge Q will be the number of electrons lost or gained. But you can lose or you can gain 1 electron, 2 electron, 3 electron, but you cannot lose 3.5. Okay, that's the meaning of being quantized. Okay, so if you go back to this example here with the balloon, see, the balloon becomes negatively charged, and you can count how many electrons you have. You cannot have 10.5, 10.3. Okay, it's an integer. So that means you're gonna have the equation. So a charge. Okay, so that will be, for example, the charge that you have on a balloon. It will be equals to. So that will be in Coulomb. Okay, will be an integer, and integer times E. And that will be the elementary charge. So 1.6 times 10 to the negative 19 Coulomb. which means you always have an integer number of electrons, lost or gained. So charge is quantized. Okay, so that will be the equation here. So this is okay. You lose 2 electrons, you gain 1 electron, you gain 2 electrons, but you cannot gain 1.5 electron. Got that? So let's take an example. If you have, remember we talked about the Van Graaff generator, that's Van Gogh. He lost his ear. He cut his ear off. Has nothing to do with physics. So let's go back to our business. So this is the Van Graaff generator. And here you can collect some charges here, right? But the total amount of charge that you can store here is very, 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 very small. Usually it's a few nanocoulomb, which means if you touch it, you're not going to die, because remember, even though the voltage can be quite high, it's really the current that can kill, because it goes for your heart, and the heart is a muscle, so it will contract. So the total amount of charge here in Coulomb is about, let's say, 3 nanocoulomb. So can you find the number of electrons here? Okay, so the total charge is 3 nanocoulomb. One elementary charge is 1.6 and 10 to the negative 19. Can you find the N? And you stop staring, you take your calculator and you hit your calculator.
Are there any requirements for calculators? Like
Any scientific calculator that you know how to use. If you don't have one with you, you can download in your phone. You know, in your phone you can download the 84, but you cannot, of course, bring your phone for the test. So nano, this is nano. So nano means 10 to the negative 9. Okay, will be integer, an integer times the elementary charge, which is the charge of an electron or the charge of a proton. Okay, and then you isolate the integer. Be careful with pandas. So when you divide with a scientific notation number. You make sure you don't forget the parentheses. And what do you get? What do you get? Yeah, times 10 to the 10, right? Okay, so that will be the number of electrons, and there is a 5. So how much electrons? So it will be 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Boom, boom, boom. Okay, so that's a lot of electrons, but the charge altogether will be only in nanocoulomb. That's why a Van Graaff generator, the one that we use in classrooms for demos, it's not dangerous unless you have a pacemaker, maybe. Okay, is that clear? Okay, so try this one for 1 coulomb. How many electrons for 1 coulomb? Same question for 1 coulomb, right? So it's 1 divided by, open the parenthesis, 1.6 times 10 to the negative 19. So 6.25 times 10 to the 18. Did you get that?
yes.
Okay, good. Charge is a property of matter and it's quantized. Mass is a property of matter, but it's not quantized. Shall I turn off the light? No? You good? It's okay? Okay, so that will be the answer. So before we get to the math, I just want to motivate you because charge distributions is everywhere in technology and in the medical field and in chemistry. So, for example, water molecule is neutral. It's neutral, but turns out that oxygen loves electron. That's why you have those ROS species, right? So oxygen will always try to steal the electrons. So in the water molecule, it will take the electrons from the hydrogen. So the molecule is said to be permanently polarized. It's polarized, but it stays polarized. So that's why the water molecule is a dipole, right? And it's a universal solvent because it's polarized. Okay, so you have a minus here and a plus here. So this is called a dipole. It's polarized. So in chemistry, you can induce polarization. So some molecules will become polarized and then they will depolarize. But some molecules stay polarized. Another example is, I'm sure you do that in chemistry, is the soap. Okay, molecule of soap. So it has a tail. So the tail likes fat, if I remember. And then the head is polarized. So it means it's going to be positive. And then there is a ion, which is potassium or sodium, okay, plus. So the head is minus, and then you have potassium or sodium, which is plus, right? So it's polarized. Okay, so it's another example. And then you have computer memory is another example. So capacitors. Okay, so in the RAM of your computer, you can store memory, but not permanently, like just for a while. So it's what is called the RAM memory, and they use tiny capacitors to store charges. So a charge will be a 1, no charge will be 0, so 10011. Okay, so this is a capacitor, very, very important in the human body. Again, biology professor, they don't want you to know that, but everything is physics, right? If you don't understand the physics, you are not understanding biology. And so, for example, when you touch something and it's very hot, right? You remove your hand. This is because you're going to have a signal traveling through your nerves to your brain, and the brain says, remove your hand, dummy. And the signal goes back, and you remove your hand. So this is because there is an electrical pulse moving along the nerves, right? And this electrical pulse happens because, so this is called, so they hide it, right? You really have to look for the physics, but actually it's really physics. It's called action potential. Okay, so action potential somewhere. I don't want to watch that. Okay, so action potential, it's because along the nerve cell, it's called the axon, right? Along the nerve cell, you have a different distribution of charges. So inside the cell, here you're going to have less positive ion. Outside, you're going to have more positive ion. So here it's going to be positive, and here it's going to be negative. So it's going to behave like a small capacitor. And then when there is a signal sent, so a pulse traveling along the nerve, what's going to happen? It's going to be depolarizing, polarizing, depolarizing, polarizing, depolarizing, polarizing. So it's like a potential that will propagate like a wave. Okay, so you have a wave moving along your nervous system, and this wave happens because those charges move in and out the cells. Okay, and this is called action potential. Okay, so people don't realize, but it's physics, right? So you see here you have the axon, your nerve cell. This is plus outside, this is minus outside, inside. And when there is a pulse, okay, that will be sent through the nervous system, the charges move in and out, in and out, in and out, and it's like a wave. Okay, so if you measure the potential here, it's going to be negative. So a distribution of charges, right? And they call that action potential to hide the physics, but it's really physics, right? It's physics too. No way around it. Yeah, you see, the potential is negative here, and then you have those little channel opening and closing. Same thing in the muscles. Muscles, they will contract because of calcium, calcium plus, right? So what's happening with calcium? I forgot. There is ATP that will make calcium move inside the muscle fibers, and inside the fiber, the protein, some protein, because of that energy from ATP, will unfold and unfold. So that will make the muscle contract and relax. So this is all because of the charges. In the heart, same thing. It has to do with sodium. Like some people say, oh, don't eat salt. You need salt for your heart. It's an electrical device and it needs that to be polarized and depolarized. Okay, what else? Printer. Printer, I can skip to, I don't know, somewhere. Okay, works also because of distribution of charges. So a Xerox machine, the way it works, you have a drum, okay, which is positively charged. And then here you have something that you want to make a copy of, and you have the light. So where you have the number here, it's like you have a shadow, but elsewhere the light will kick out the charges because of the photoelectric effect. And then here you have some, the tuner, right, with ink, powder that will stick here, and that's how you get a 3, right? So that's how it works. And you need to have a discharge somewhere to charge the drum. So this is also electrostatics. Without electrostatics, there is no copy machine. Okay, so that's another example. What else? The heart works also because across your heart you have a plus and you have a minus, right? So there is a voltage across, and then it gets polarized, depolarized, polarized, depolarized. So that's how it works. Antenna, right? It's also because of a dipole, plus and minus. So let me show you how it works. So for example, here you are broadcasting something, and there is an antenna here. So here you have an electron, and the electron will be push and pull because of an electric field. When the electron goes down, you're going to have a minus, so that will be a plus. So again, polarization, depolarization, polarization, depolarization, and that's how you're going to generate an electromagnetic wave. So I can show you that. See, it's also minus and plus, and then minus and plus. So it's also moving charges in that case, but it has to do with charges, right? And you have the electromagnetic wave traveling, and here it will, if it has the right frequency, so you need to have resonance, then it will make that electron wiggle at the same frequency, and then with the magic of electronics, you turn that into a sound. Okay, so what is camera sensors that we all use? Same thing, has to do with turning light into an electrical signal. I don't know if I have a picture somewhere here. So these are the cheap ones. These are the most expensive, but it's the same idea. So this one is what you use for your phone. So you have a photons, you have light that will kick out a charge. Okay, so the charge is held in the transistor, and then that will turn into an electrical signal, like a voltage. It's not exactly the same technology for CCD, which is more expensive, but the same idea. Okay, light will kick out some electrons, and the electrons will be collected there, and you have something to amplify the signal. So this is all static electricity as well. Okay, a thunderstorm also. charges, distribution of charges. So in a thunderstorm here, you see, you have some rubbing happening, friction. So you're going to have negative on one side. So if you have negative here, so inside the ground, I told you the ground is a big reservoir of charges, so that will become positive. And if the voltage is large enough, you're going to have a discharge. Or you can have a discharge between two clouds. Okay, so same idea. Okay, what else? Okay, this you already know. Protons inside the nucleus, the soap, we already talked about that. And power lines also picking up a lot of static electricity, which can be an issue with the corona discharge because the charges tend to build up, right? So anyway, that's for the motivation. Okay, so you have conductors and insulators. Well, we already talked about that. So the same way that heat goes from warm to cool, then electron, for example, that will make up the electric current goes from high potential for them to low potential. So anything in nature wants to go from high energy level to low energy level. Like you do, like all of you go back to the same seat. Less energy to find a new seat. Yeah, I think it's better like this. Right? It's called inertia. Okay. So this is all conceptual. What else? Okay, we did that. So if you have two insulators, okay, and you rub them against each other, you are doing work. That's what we did last time. You can separate the charges. Okay, so you can separate minus from plus. So it means there is always one that will like electron better than the other one. So in that case, this here is some kind of rubber. So it will like electrons better than fur. Okay, so this one will pick up electrons, this one will lose electrons, but the total charge will stay the same. Now those charges here, they cannot move. They are glue wherever they are because it's not a conductor. If it was a conductor, then the electrons will start to move as far as possible from each other. Is that clear? Yes.
What determines which one keeps the positive and which one keeps the negative?
Okay, that's a very good question. There is an affinity hierarchy. So, for example, if you do fur and rubber, the rubber likes electron more than fur. So you can compare how tightly they are holding on their electrons. So if you do, and I think it's also a conceptual question, if you do silk and glass, the silk takes the electron. So they always do this experiment. Fur and rubber or balloon, the balloon takes the electrons from the hair, for example. But if you do glass and silk, silk takes the electron. Okay, so there is like a hierarchy. And engineer, it's done by engineering. Okay, they make those special tables to know which one will take the electrons, which one will give away the electron. So that's a good question. Okay, so the same way you have conservation of mass, you're going to have conservation of electric charge. So even though you have minus here, plus there, the total amount of charge will stay the same. You know that from chemistry, right? So just to give you an example, because I don't like chemistry, so I took an example from radioactivity. So if you have a radioactive sodium, so it's radioactive. So I think here it's 22 atomic mass. The atomic number is 11. So that means how many protons? 11. And how many neutrons? 11. So it's not happy, right? It wants to decay. It's radioactive. So it's gonna decay in neon, which is stable, so it's not radioactive. And here, are we okay or not okay? Are we okay? Or not? How many protons do we have? And 10, so we are missing what? What did you say? Hydrogen? Okay, it could be hydrogen, yes, but not in radioactive decay. You don't have hydrogen. You can have alpha particle, beta particle, or gamma particle. But it's a good guess. So instead, we cannot have an electron, right? No, we cannot have an alpha particle. So alpha particle is just helium. Helium has 2 protons, so it doesn't work, right? What's the opposite of an electron? So no, it's not a proton. A positron, exactly, which is an anti-electron. So it smells like an electron, it looks like an electron, but it has a positive charge. So they use that, and then here you have a neutrino. So they use this one. They use this one for a PET scan. It's called a beta plus decay. So when you are doing a PET scan, they give you some radioactive stuff to ingest, and God forbid you have a tumor, it will go to the tumor because you mix that with sugar. A tumor always is hungry for sugar, right? So it goes to your tumor and it's going to decay with a positive electron. Inside the tumor, the positive electron is going to combine with electrons because we are full of electrons. And what's going to happen? Huh? Neutralize, annihilate each other, boom, destroy each other. And because they destroy each other, you're going to have gamma rays. So that's how you can highlight the body, right? So you have positron going to the tumor, God forbid, and then they annihilate with the electron, and you're going to be highlighted by gamma rays, and you can see what's going on inside. So this is a PET scan. So they use that for PET scan, but not for human. They use that to look inside material, for example, right? So it's a tangent, but you get the idea. So that way I avoid examples from chemistry. Okay, so conservation of charges. So now electroscope. So that's what I was talking about. You need to know that for assignment. I forgot for the test or not, but if you have fur include hair. Usually the experiments were done with cat fur. I don't know why cat, but cat fur. That's it. Used to do that. And here it could be like rubber, like a balloon. Then the electron will always go to the balloon. So the balloon, the rubber, likes electron more than fur. So if I rub a balloon, if I rub my hair with a balloon, the balloon will be negatively charged, my hair will be positive charged. But if you do silk and glass, it's the opposite. The glass becomes positively charged and the silk will become negatively charged. So that's how it works. Yes.
Can you do like silk and fur?
Silk and fur. Not sure. I never tried. I'm sure you can.
Which one do you think would be the one of the
I have no idea. We need to ask. The silk. It's a good question. The silk likes electrons more. See, there is a hierarchy. There is a table. Thank you, Gemini. Okay. So if you touch a conductor here, you see the electrons, they don't stay glued like they would on a balloon. They're going to spread out, okay, always on the outside. Electrons cannot stay inside the conductor. Okay, so if I get charged, because I rub my feet against the carpet here, the electrons will stay on the outside. Okay, so here I think I'll show you this demo. It's like a mini Van Graaff generator. Yes. See, it's not charged. This is a conductor. Oh, did you hear the spark? Oh, I felt the spark. It jumped. It jumped on my hand because it wants to go to the ground. See that? And it's holding the charge if it's not too humid. Okay. So with a conductor, the electrons can move as far as they can from each other. It depends on the geometry. Now, if I touch it, that means I ground it, right? And the electron will move through my body into the ground. Yes.
Reason they go to the edges because they don't want to be close to each other with the conductor, right?
Yes. So in a conductor, they can move. So because they can move, they will move as far as possible from each other. And if you compute the geometry, and they will they like to be at the sharpest place. When it's sharp, you're going to get more electrons. Okay. Well, I will see that later because I don't know what. Oh, yeah. You see, for example, if you charge knife, you're going to have more charge here at the edge. So each time it is sharp here, then you're going to get more charges. So when you have a rod, for the thunderstorm, at the end it's going to be very pointy because you can collect more charges. Okay. So I don't know if I can show you that. Problem with demo is that sometimes it works and sometimes it doesn't work. Hi. Can you do this? Let's see if it works. Just put your finger. No? You don't think what was it? Yeah. Maybe I do. With the Van Graaff generator, it was more fun because I could shock students more efficiently. Okay, so that won't be a surprise for you. Like charges will repel, unlike charges will attract. Does that make sense? And I can show you that with a short demo. If it works, sometimes my demos don't work. So how does it work? Okay, so I'm gonna rub this one with silk. You with me? And silk loves electrons, right? So the silk become negative charge. Okay? And then another one, the same material, also with silk. So what do you think is going to happen? They should repel if it works. Oh, look at that. Isn't that amazing? So this is called force at a distance. Okay. As long as you have a force, you have an acceleration, F equals ma. And actually, it's more like an electric field. So two electric fields interacting with each other, pushing each other away. Now, if I change and I take glass, it will be, let's see if it's the opposite. So the glass will become, so this is negative. So the glass will become positive. So negative and positive should attract. Ooh. Well, why don't you say, oh, look at that. Isn't that amazing? Okay, it has, it's like a flying wheel, right? It's storing spinning energy. Okay, so that works. Maybe I'll do that after. Sorry, thank you. Okay, so what do you think? So you have a plastic rod with charge with a wool cloth. So plastic becomes negative. So what do you think? Oh, you cannot see. Okay. So you have a conductor. So this should be. It's not a conductor here because you want to isolate. That's a sphere. Supposed to be a sphere. And this is negative, 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 negative. You touch it, right? So because you touch it, it's a conductor, then it will become negative because electrons can move on the conductor, right? As far as they can. So you move away. So now do they attract or repel or what? Repel, right? If they have the same charge, they will repel each other. Oh, that's a demo which is very famous by Walter Levin. So this, we are talking about 10,000 volts, right? So he's going to stand here. So that way he's going to be isolated from the ground. So when he's going to touch the Van Graaff generator, the charges is going to go through his body, but it cannot go to the ground. So if you are not connected to the ground, then you will be fine. You are not going to be shocked. It's only when you make that path to the ground that you'll be shocked. But here is isolated, right? You have to be careful because if you collect too much charges, you're gonna have a discharge. See that? So all the electrons, okay, they move as far as they can, and because they have more place to go, they move through his body on the outside, also for the stencils here, and they repel each other because they will be charged uh, the same charge. Okay.
Explain why it has to be standing like off the ground or else you can go through the circuit.
Yes, exactly. So the ground is like the base, right? So if electrons always wants to go to the ground, so if you isolate yourself from the ground, you cannot be electrocuted. So you know the high tension lines, right? You see the birds, and they are not isolated. It will be too much money, right? They don't have anything around. So the very high voltage line, if there is a bird, it doesn't get electrocuted because it's isolated from the ground. If you touch it, you're gonna be electrocuted because in that case, if you touch this, right, what's gonna happen? This is connected to the ground somehow, here, let's say, no, it's not connected to the ground, but if you touch it here, let's say you touch it, all those electrons are going to move through your body and go to the ground. So you close the circuit. The small one, no. From this one, I don't think so. Because even though it's a very, very high voltage, you don't have enough charges. So it's really the charge, the number of charges that kill. It's not the voltage. It's the current that will kill you, not the voltage, right? So electricians, for example, they have their hand in their pants and it's connected, like they have a way to do it. So if they are electrocuted, it goes through their hand up, down to the ground, and it keeps the heart. It's because of the heart, yes. The air. I don't understand the question. Yeah, yeah. Oh, why they cannot go to the air? Okay, that's a very good question. It's because the air is not a conductor. It's not a conductor up to a certain point. So actually, what makes the electron move is called the electric field. So the electron will love to jump to the ground. They will love to go through the air, but for that to happen, you need enough voltage. And when that happens, yes, it will jump through the air and it will go to the ground, and you have what is called a discharge. Okay, so if you go really close to it, even if you don't touch, right, and you are touching here the ground, so here it's going to be all positive, especially your nose. Let's say here has a big nose, so a lot of positive here, positive, positive, positive. So they really want to get together, but they can't because it's not a conductor up to a certain point. When the voltage will be high enough, there will be a spark and all those electrons will go to the ground. Okay, so this is called charging by contact. Okay, and again, inside here you have no electron, you have no charge. And then, so that will be the Van Graaff generator. And then you have something called charging by induction. So maybe you will do that for the lab. So for example, if you bring here, that will be negative, but you don't touch it. Then, because remember, electrons are free to move inside a conductor. Okay, they move around and they are not tied to their nuclei. So if you bring a negative rod here, the conductor will get polarized. So it's going to be positive on one side, negative on the other side. Okay, and then you can ground only this side, so you get rid of the electron here because it's connected to the ground, and those here are holding there, and at the end it becomes positively charged. Okay, so this is charging by induction because you are not touching it. Yes.
Basically, by connecting the sphere to the ground, you basically depolarize it.
Yes, it's what I'm doing here, right? Because the electron they want to go to the ground. So this is charged, right? And if I touch it, boom, I felt something, and all the electrons go back to the ground. But here they are attracted to each other, so it's going to stay there. And because it's a conductor, once you remove the rod, they will spread out far away from each other. Yes.
Uh, in when you touch the rod, or sorry, when you connect the grounding wire, by depolarizing the sphere, do you also charge it?
Yes, it's being charged. That's why it's called by induction. It's not that you are charging it, it's that at the end you're gonna have more plus than you have minus. Because some minus have left to the ground and the plus they were trapped here because they're attracted. Okay? So yes, you are depolarizing it and it becomes positively charged. Okay, so there is an experiment. I used to do it, but it's called the electrophorus. So if you want to do it for a demo, you can have a video here to show you how to do it. You need you don't kill your cat. So they used to do that with a cat fur, and then now it's rabbit fur, but rabbits are cute, right? So you can do it with a piece of wool. Okay, that works too. Okay, or silk. Okay, if you have a tie made of silk, it works also. So I'm not going to explain it, but the idea is the same. It's charging by induction. I invite you to watch this video. Okay, if you want to do the demo, that will be cool. Okay, and about polarization, because it's so important in chemistry as well. So here, let's go back to my balloon. So the wall is an insulator. So it's made of molecules, and the electrons are not free to move. If it was a metal here, like a plate made of copper, if I bring the balloon close to it, all the electrons will move away because they are free to move. They are not full. They are not tight. But in that case, you see, it's an insulator. What's going to happen? This is called polarization. So even though the electrons cannot move freely, the molecule can be polarized. And that's how it's sticking to each other. Yes.
With the metal sphere and then the ducted stand, the electrons wouldn't go to the ground unless you had the connecting wire.
Yes. Yes.
So,
Except if it's very humid, so then the electron will jump on the water molecules, right? Because it's water molecule is like polarized. But if it's dry, then you can hold it for a very long time. So this is called polarization. Okay. So for example, typical experiment, you take a piece of paper here. The paper is not charged, and the paper is an insulator. But if you bring a comb, you comb your hair, and it's so the comb becomes negatively charged, and then you can pick up some pieces of paper. Oh, here it is. But the paper is not charged. It just gets polarized. So one side will become positive, one charge will become negative. Only the comb is charged. Okay, so I want to show you that. I don't know if it works. I am the only one to do demo because it's very embarrassing when it doesn't work. Okay, so you have this is neutral. Do you agree? Okay, so now is it attractive? Because it gets polarized. Very good, it gets polarized. But if I touch it, and this is a conductor, what's going to happen? Repel each other, right? If it works. You see? I can do that all now. They have a butterfly, so I never tried. So we tried the butterfly.
So you tried to it became depolarized?
Yeah, because it became, if this is positive, we don't know, right? So that's another thing. With the Van Graaff generator or static machine, we never know if it's positive or negative. But let's say it's negative here, if it's negative here, it's positive there. But let's say it's negative, when you touch it, this one becomes negative as well because it's a conductor. So the electron will move all over. If it was insulator like a balloon, it's much harder to convince the electron to move on the balloon. But this is a conductor, right? And I don't know, it wants to go to me because I'm connected to the ground. But the first one worked, okay? That's fine. So you can try that with your cat. You rub the balloon, it becomes charged, and then it is attracted because of polarization. Okay? So Van Graaff generator, you have a huge one. You can see them at Boston University, not Boston University, the museum, the Science Museum at Boston. The first one was built at MIT in 1933, and the first ones were used as accelerator to accelerate the particle because they can generate a huge voltage. And then it's fun because it can be discharged. So in that case, it's going to go through the air. Okay? Are you still there? So John Travolta again. See, he's rubbing his feet. The electrons don't stay there, okay? It goes inside because he's a conductor. But little by little, they're going to spread as far as they can from each other on the outside. And they are very upset because they want to go back to base, which is the ground. And here they find a way. And the voltage is high enough that the air will become a conductor. It gets ionized. That's why you have light. Okay. So that takes us to Coulomb's law. So his name was Charles Augustin de Coulomb, and he was French, obviously, 1786. And he found, so he didn't really find because he was inspired by Newton, the law of gravity. So if you remember from physics 1, okay, so from physics 1, if you have two masses like m1 and m2, and that will be the distances between the masses, okay, they're gonna attract each other. So gravity is always attractive. And remember Newton's third law, the force will be always the same. You cannot pull without being pulled, and you cannot pull harder than you are pulling. So the force is the same even if m1 is more. And the force of gravity between two masses is the constant here, which is a very small constant m1, m2, over the distance square. And this is called the inverse square law. So it's a typical conceptual equation. If you multiply the distance by 2, the force will be divided by 4 because you have a square, inverse square law. Okay, that constant here is a way to tune the gravity. Okay, to tune gravity, which means gravity is very, 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 very weak. So it's going to follow what we call an inverse square law, right? Inverse square law. And this is because actually it's not really a force at a distance. There is a field, a gravitational field. So if you multiply the distance by 2, okay, you see gravity is going to spread out more and the force will be divided by 2. If you multiply the distance by 3, the force will be divided by 9. Okay? So we have the same thing for charges. So if you have a charge Q1 and a charge Q2, if one is negative and the other one is positive, they're going to attract each other. The force will be the same in magnitude because for every action you have a reaction, and it will be exactly the same format. So here you need what? What do you have here? A constant, very good. We have an electric constant that will tune how strong is the force. But here we want a very strong force. Why? Because otherwise we will not be held together. Okay, the only reason why we are held together is because of the electric force. So we want something very strong. Okay, and then here, what do we put? Yes, and then charge 2 over exactly R square or D square. Okay, so this is called Coulomb's law. Yes.
What's the when you wrote the force under? What are the numbers you wrote next to it?
Here?
No, no,
Where?
above
Here?
the charge one, charge two.
That means negative. So this, I suppose this one is negative and this one is positive. This is F12, this is F21,
Okay.
and the magnitude is the same. Is that clear? So Coulombs, he copied Newton, right? But he's the one who found that constant. So whoever is in charge of the universe decided that gravity has to be very weak, so we can walk around and not crawling. But the electric constant has to be very big. That's why we have a shape, right? So everything, like if I try to lift my notebook, I can because it's very easy to defy gravity. But if I try to pull off my finger, I can't because of that electric force, right? It's the electrons that will be providing the glue, holding my finger to my hand, and this is lucky because I don't want to lose my finger. That will be terrible. So the electric constant is very large. Okay, so Coulombs, Charles Augustin Coulomb, he did that experiment, and it's the same thing as the Cavendish experiment, who computed the gravitational constant. So he did that experiment to find this constant here. And it's easy to understand, right? So this one will be charged, let's say, positively. This one is charged negatively. They're going to attract each other. So here you're going to have a twist, okay? It's like a wire. This is a wire. It's made of like a fiber. It's going to be twist, no? Something like this. And the angle will be proportional to the force. So it's like Hooke's law. So that's how he did it. Right? Any question?
So that's the constant 8.99.
Okay, so the constant is about 9 times 10 to the 9. And you're going to see as we move forward, you're going to see that they have a different way to write it down, especially your textbook. So you can say the electric constant is 9 times 10 to the 9. And then you have some unit. And it's also equals to 1 over 4 pi epsilon 0. And epsilon 0 is 8.85 times 10 to the negative 12. It's called permittivity of vacuum, the vacuum permittivity. And if you look at your, let's look at your equation sheets. Let's see. Or maybe the other one, right? You had the constants. It's not on the other, maybe on the other one. Do you see it on the other one? Oh, okay, thank you. I didn't see. You see, epsilon 0 is 8.85 times 10 to negative 12. Electric constant is 1 over 4 pi epsilon 0, which is 9 times 10 to the 9. Okay? Agree? And you have the charge of an electron, the mass of an electron, the mass of the proton. So it's very useful. So for electrostatic, we're going to use epsilon 0. And then for magnetism, we're going to use mu 0. Okay, so it's just a definition. And now I'm lost. Okay. So again, it's an inverse square law. Inverse square law works for gravity. It works for light. It works for radioactivity, radiation. So you have a source here. So in our case, it will be an electric field. We're going to see that. But you see how it's going to spread over a larger and larger area. So for the same unit area here, you're going to get nine times less force. Okay? So you have the inverse square law. Gravity works the same. So here, if you're on the Earth and the mass is 400 pounds, if you multiply the distance from the Earth by 2, your weight, instead of being 400 pounds, will be 100 pounds, right? You divide by 4, and so forth, and so on. It's an inverse law, 1 over the distance squared. Okay, so try that. It's a conceptual question. Van Gogh again. Okay, so the force is proportional to Q1, Q2 over the distance between them square. So this one is multiplied by 2. You cannot solve anything by staring. Staring is not your friend. You have to take your pen and your notebook or your tablet. You cannot do it in your head. So what is the answer? C, very good, right? So for example, if you are taking the MCAT, that will be a typical question because the MCAT now is more conceptual. But by the way, you cannot have the calculator now. They don't, not in my class, but for the MCAT. Okay, so let's try to do this one. So this is one model for the hydrogen atom, which is simplification. It's not really what's happening because the electron is not really like a particle, right? It's more like a particle wave. It's more complicated than that. But let's pretend that the hydrogen atom behaves like a planetary system. So you have the proton here and the electron, and it's a uniform circular motion. Remember from physics 1, okay? Circular motion here. And they want to find the speed using what you remember from physics 1. So you have an electric force here, pulling. Okay, that force is perpendicular to the velocity. So that force cannot make the electron go faster or slower. It's just changing the direction. Okay, so you want to keep going in straight line at a constant speed? No, you can't. I want to go in a straight line at a constant speed? No, you can't. So this is called a centripetal force. Okay, so that means in magnitude, it's going to be mv squared over r. Are you with me from physics 1? This is a circular uniform motion. The centripetal force is only here to change the direction. Okay, so you can do that now. First let's find the force. Let's apply Coulombs law and find the force, and then we will find the speed. Don't stare. Do it. You can talk to each other, right? When we are doing for the problems, if we are doing problems, you can talk to each other. you just plug it in. Okay, so the electric force is the constant, always put parentheses, and then Q1 will be the proton. The proton has a charge of 1.6 times 10 to the negative 19. And then the electron has the same charge, right? So you square it. And then here you open the parenthesis and you have the distance, but you have to square it. Don't forget to square it. Yeah. 1.9. I don't know why it says 1.9. It should be 1.6, no? It's 1.6. I don't know why it says 1.9. It's a typo. 1.6. Thank you. Okay, so do it. More you do in class, less you have to do at home. Do it with your TI. Do you want me to do it or do you need help? Yeah.
What letter did you put next to the MD equation?
Here?
Yeah, what letter?
This?
Oh,
This which letter?
the FD equation, the one written in red.
mv square over r.
Oh,
The centripetal force, right? The centripetal force equals the mass times the centripetal acceleration, which is centripetal acceleration is the speed square over r. Okay, so that's for circular uniform motion. What? No, it's not interchangeable. This is something else. This is Coulombs law, okay? And this is from physics 1. So physics 1 says that when you have a circular uniform motion, when something goes around a circle like this, so for example, you have the Earth and here you have the moon, that means you need to have a force here pulling toward the Earth. And that force is called a centripetal force, and it's always the mass times the speed square over the distance.
so the 1.6 that one chart is multiplied, right?
Yes.
How come it's not blue?
Okay, because in that case, I only consider the magnitude. Because I see the direction here, and the force is a vector, and the direction keeps changing. It's not pointing in the same direction. So this is just the magnitude. That's why you always need to draw. Okay, you always want to draw. Okay, so did we find out? So what did you get? 8 Newton. Do you all agree? Yeah? Did you save your memory from last semester? You have to save your memory, right? So the force in magnitude equals mass times the velocity squared divided by the distance. Do you agree? So you can find the speed. Can you isolate the speed? So this is a centripetal force. Okay, mass is the mass of an electron, so that will be 9 times 10 to the negative 31. The speed squared over the radius, which is what? 5.29 times 10 to the negative 11, which is equals to the force. And you can isolate the speed. Agree? So this is from physics 1. It just says for an object to stay along a circular path, you need a force to pull the object toward the center. Otherwise, because of inertia, off tangent it wants to go, so you need a force to pull it back on track. And that force always have this expression, mv squared over r. Yes.
Can you explain the first equation you did? I don't understand that part.
This one?
Yeah.
That's Coulombs law.
Why are we applying it in this case?
Because they attract each other.
Okay.
So each time you have charges, they either attract or repel. So in that case, they will attract, and Coulomb's law says that that will be the expression. 9 times 10 to the 9 times 10 to the 9 q1 times q2 over the distance squared.
But what were we trying to solve for?
We are trying here. The first question is to find the force. So you find the electric force between them. They attract each other. And then second, you use that to find the speed, because that will be equals to the centripetal force.
You say the last part again? So we're finding the force after plugging into the.
So then you use that to find the speed, because that will be equals to the centripetal force.
Can I see the problem again, please? Can I take a picture of it?
Huh?
Can I take a picture of the problem?
Sure, you do whatever you want. It's recorded, right? And you isolate for the speed, right? So what you get? Oh no, I didn't find 2. 2? 2 times 10 to the 6? No? Yes? Meter per second. Okay? Is that clear? So from physics 1, don't forget your physics 1. Remember when you have, like, let's say you are holding like a toy and you make it spin. Okay, let's say you're holding a toy here and you make it spin in a circle. That circle has a radius r. Let's say it's a stone. Maybe you are David. Okay, this is David. And this is a stone. And that goes around a circle. The stone has inertia. So it wants to keep going along a straight line at a constant speed, but no, it can't, because there is a string. Okay, so you're going to have a force here. That force here, okay, is keeping that stone on the circular path, otherwise off tangent it goes. That force here is always the mass times the speed squared over the radius. In that case, that force providing the centripetal force, in that case, is the tension in the string. And that's called the centripetal force from physics 1. So in that case, the centripetal force is provided by the attracting force between the proton and the electron. Okay, the electron wants to go bye-bye. I want to keep going along a straight line at the same speed. No, it can't, because there is a force here. Okay, it's an attractive force. That force will be the centripetal force. Okay? Okay, so here you see F equals ma, centripetal acceleration, mv squared over r. Is that clear? Okay, so let's do something now. We are still working with the hydrogen atom. This one?
No, the answers I couldn't write it down.
But yeah, but you know it's in my PDF, right? It's in my Dropbox. Okay, so let's now they attract each other because this one is plus, this one is minus, but they also have masses. Do you agree? So they attract each other because there is a gravitational force as well, M1 and M2. So can you find the gravitational force between the proton and the electron in that same case? Okay, so the proton and the electron, they attract each other because any mass attract each other. So I want to compare the gravitational force with the electric force. So can you do that? Can you do that computation? Okay, so you have M1, M2, electron, proton in the hydrogen atom. You have the same distance, and you want to find that gravitational force. Okay, so it's just computation. You just plug it in. There is nothing scary here. You're just plugging in. And you have to take your TI and you have to do it in one shot. It should not take so long. The mass of the proton is given. Where is the mass of the proton? This is yes, 1.673 times 10 to the negative 27 kilogram. Okay, so the gravitational force is the constant, which is very small, 1.67 times 10 to the negative 11 times mass 1. Let's say it's the electron, so 9 times 10 to the negative 31 times the mass of a proton, which is 1.67. You can forget about the 3. Okay, over the distance square. Okay, so the gravitational force is, are you doing it? See, look, I'm going to do it for you. Maybe you are tired for all this very long break, but look, you have to do it in one shot. One shot. Minus 11, you close the parentheses, open the parentheses, 9 times 10 to the negative 31st, you close the parentheses, open the parentheses, 1.67. This is base 10 here. If you do second comma, that will be base 10 minus 27. Okay, close the parentheses, enter, and then you divide and you open the parentheses always. 5.24 times 10 to the negative 11, up, up, up. Did you get that? 9 times 10 to the negative 48. Okay, if you need help with the TI, let me know after. So 9 times 10 to the negative 48. And what was the electric force? It was about 8.2 times 10 to the negative 8. So which one is stronger? The electric force, right? So you can forget about gravity when it gets to a very small scale. Gravity works only for planets and black holes and stars. At a very small scale, even you attract each other, but you cannot feel it, right? Because gravity is so small. So between them, we are talking about a factor of 1040. So how stronger is the electric force? It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 22, 43, 34, 5, 6, 7, 8, 9, 10. So it's a big factor, right? Yes.
Why is the G constant here?
The G?
Yeah. But you 6.67 versus 1.67.
Maybe I did a mistake. It's not 1.67. Maybe it's 6.67. Oh, there was a typo again. But it's fine. In that case, it will be fine. It's just for the sake of the computation. But let's look here. Yeah, you're right. It should be 6.67. Okay, there is a typo here. It should not be 1.67. It should be 6.67. But it's fine. The ratio is the same. It's going to be the same. It's about 10 to the 40. Thank you. Any question? Okay, so that will take us to adding vectors. So make sure you review that. Okay, in Dropbox, you have 2 tutorials. Otherwise, if you don't remember how to add vectors, you're going to be totally lost. So make sure you review how to add vectors in 1D and in 2D. Okay, so it's typical question. You need to know how to add vectors. And again, you have 2 tutorials in my Dropbox. Is that clear? So good, thank you. And just to start here, and then we'll do that on Tuesday. But it says here, find the magnitude and the direction of the net force on Q1. So when you're going to have a problem like this, first of all, you isolate your system. So Q1, you are interested in Q1. So Q1 and Q3, do they attract or repel? So you're gonna draw here. That will be the force between 1 and 3. And then Q2 and Q1, do they attract or repel? Attract also, but this 4 is smaller than 7. You're gonna do something like this. So the net force will be to the right because you are adding vectors. But this is a 1D problem, so it's going to be easy. Then the next one, here I will get back to that, but the next one will be in 2D. So that's why you need to review how to add vectors. You can go back to Physics 1, the beginning of your textbook, or you can use the tutorial.